P was born in the field of ultrasound, and for ultrasound, the human body was basically a water, because the ultrasound propagates at the speed of water, more or less. So it was considered as a fluid a very, very long time. And during the 90s, suddenly we discovered that no, we were a solid, so the shear wave could propagate inside the human body. But we are not as stiff as that. We are more like a soft solid, like that. And in this case, the compressibility is way higher than the shear elasticity. And there's two consequences of that, for that. First, there's a huge speed difference between the P wave, or the ultrasound, and the shear wave, only 1 meters per second, up to 10 meters per second. So this huge difference is important, because then we can use P wave or ultrasound to follow the shear waves in soft tissues. The second consequence is that because it is important in medicine to use palpation, the physicians always try to palpate in order to feel strange things like cancer nodules. So the elasticity that we can feel with fingers is not at all related to the compressibility. It is way too higher for our sensors. What we can feel with fingers is related to the shear elasticity. So making an image out of shear waves, which is elastography, is a way to conduct a palpation tomography in soft tissues. So I won't go through all the history of elastography. There is two, I will just mention this date, because 87, Krusskopf was the first to use ultrasound Doppler together with monochromatic vibration at low frequency, and he was able to follow for the first time the shear waves, and it is mentioned in his paper. All the technique used monochromatic vibration, or static, but I won't speak about that. And then Matthias Fink, during my PhD thesis, had the idea to replace the monochromatic vibration by a pulse, and a pulse contained much more information, and it was the beginning of pulse elastography, which is generally encountered in clinics now. So this is the global idea here. When a clap reaches the belly like that, you can see that it creates seismic waves at the scale of soft tissues, and we can see here the Rayleigh wave front. And if we have created a Rayleigh wave, it means that there are bulk waves, compression wave, and shear waves. So the idea is to follow the shear wave propagation inside organs in order to retrieve the elasticity from the speed of the shear waves. But in order to have such a movie, we need an ultra-fast camera working at 1,000 frames per second or more. And it was not possible at that time when I started my PhD thesis, because commercial ultrasound only work at 25 frames per second. This is enough for the physician to see in real time how the heart is beating, for example, but it's not enough to follow the shear wave propagation. So we had to change the way imaging echographic devices was working. And we had everything in the lab. We had the so-called time reversal mirror, which are basically electronic that can control all the transducer of a medical array. And then we totally changed the way imaging was done, and we could reach frame rate as high as 1,000, 10,000 frames per second. So I will quickly go through this, but it will last a long time if I go going in the detail. Here there is the echographic devices made of 128 transducer, and we send a short pulse from the front face. So the front pulse propagates in tissues, and during its propagation there's a lot of scatterers, and what we can see here is what we call the ultrasonic speckle on 2 millimeters depth. We make a zoom, and if we send 2 pulses, we have exactly the same realization of acoustic speckle. Now, if the medium is moving, for example, because of a shear waves, then the acoustic speckle is going to move back and forth, and we are able, with speckle tracking algorithms, very close to Doppler technique, we are able to measure on each point of an echographic image the displacement field. So now I won't speak anymore about ultrasound, but you have to keep in mind that we are able to follow the displacement inside soft tissues as if we were able to put geophones everywhere on the image. So this is the results here on 8 centimeters depth, and here the front face of the ultrasonic array send ultrasonic pulses and at the same time give a clap, and then we can see here the shear wave propagation, almost planned shear waves. And here in the middle we put in this soft material an inclusion, and we can see that the shear waves is disturbed by that. So now we are going to measure the speed of the shear waves everywhere, and we are able to reconstruct tomography, which is here, and we give to the physician in kilopascal the shear elasticity map with here 2 inclusions. Okay, so in clinics we can, the first application of elastography was the FibroScan. So we just measure the speed of the shear waves in the liver, so we give a knock, and with ultrasound we are able to globally measure the shear wave speed, and it gives to the physician information about the fibrosis, and the final stage is the cirrhosis. And later, supersonic imaging put in the market these echographic devices with ultrasound image together with elastographic reconstruction here. So now I would like to show you that we can use time reversal and mixed time reversal with elastography to have a passive elastography technique. So I will briefly introduce some basic idea of time reversal. So again, this is a pool, and if we send an object here, we create these waves, and around the pool there's a lot of mechanical paddle able to record the waves there. And each mechanical paddle is related to an electronic, an independent electronic. This is the first step of the time reversal experiment. In a second step, we time reverse the signal in the memory and then use the same mechanical paddle as emitters, and only this mechanical paddle was working during this experiment. Not this one and not this one, but it does not change the experiment, or almost. And we can see some strange fluctuation at the surface of the pool, because we send first the waves that arrived late, and we send late the waves that arrived first. So I can say one word about this pool. It was shot, this movie, in Sao Paulo, Brazil, where one of my PhD students, Nicolas Perez, did his postdoc, and he tried this experiment. But in this pool, they are testing the wave effect on an offshore platform that is supposed to be here, but it's not here. And then they test the mechanical resistance of this offshore platform. And at one point, we can see that the waves reconstruct, and we observe here the converging wave that is going to focus exactly where the object was thrown, and the conservation of energy make that we can see now the diverging wave. So this is time reversal. We have a source in a medium. It can be complex, anisotropic, inhomogeneous, but if we can record the field in a closed cavity, we know how to focus back to the source. So the idea is that the waves still have the memory of the source. And I'm going now to show how it can be used here, but before I'm going to mention this experiment. We talked about that this morning, the experiment of Carsten Draeger. The problem with time reversal is that we need a lot of sensors. We need to put sensors in a closed cavity. So what we did experimentally was to take only a part of this time reversal cavity, which is a time reversal mirrors. But we can go even further and use one point, and this is the experiment of Carsten Draeger, and Julien Duroni worked on that too. So this is the experiment. Quickly, from point B, we send a pulse in this chaotic cavity, a plate, and on point A, we have a long reverberating signal due to the ultrasound that are trapped in this 2D in this cavity. We time reverse this signal. which look like noise, and a part of the wave start to converge back to the source, and with a laser interferometer we are able to observe exactly what we've seen in the pool. So we have the converging wave here, the spatial-temporal collapse there, and the diverging wave there. And what is important in the following is that the size of this focus spot is limited by the diffraction law, and it has the size of half a wavelength. So now I'm going to do the experiment, so I have to use MATLAB. So I'm going back here, and I have here two microphones, so that I stuck as I could with this, but these are the two microphones that are connected to an external sound card which is there and which is connected to my computer. So I'm going to put them back like that, okay? And now when I knock on the table, I have two signals, a green one and a blue one, because when I knock, I create sound that are directly catched by the two microphones, and we have also this part of the signal, reverberation, or it is the coda wave. Now I'm going in the first step to put in the memory of the computer the acoustic signature of 6 points that are there along this cross. So this is the first part. I have to knock twice on the same point, and then we can hear that he understood that he had to keep that in memory. 3, 4, 5. Now I'm going to do the time reversal experiment, but I won't really send waves inside. I will use correlation to compute the field that we would observe in a real time reversal, since we can show mathematically that time reversal is a spatial-temporal correlation, so MATLAB can do the correlation. So when I knock on point number 1, then the computer with correlation can see that the maximum of the field, of the time reversal field, or of the correlation, is on point number 1. So you can see here that he recognized that I knock on point number 1. Now I knock on point number 2, 3, 4, 5. So what is it useful for? So now I'm going to use another point, and then I have this software. And now, after some manipulation, I should be able to control this software. When I knock on point number 1, the computer knows that he has to play the music. On point number 2, to stop it. On point number 3, I switch to the second music, or I can come back with point number 4. And when I'm fed up with that, I just knock on point number 5. So we can transform any object as a remote control, since what we need is only that acoustic wave propagate. But this is realized for any dense material. We are only using here one small part of the information of the time reversal field, only the maximum of the spatial-temporal collapse. But we have other information. The size of the focus spot is related to the wavelength. So we can measure the wavelength, then we know the frequency, so we deduce the wave speed, and the wave speed is related to the elasticity. So now I'm going to measure the elasticity of this table. So I have to change